AC.
Good afternoon to all. Myself, Ramani Krina, PhD Research Scholar at Department of Physics, Saurashtra University. Welcome you all on this platform named Vigyan Yatra, a travel for scientific Indian minds towards Vikshit Bharat. Vigyan Yatra is a series of conferences sessioned from March 4 to 15, 2024 and is jointly organized by Department of Physics, Saurashtra University, RAJKOT, Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati, VIBHA and GUJCOST, Department of Science and Technology, DST, under Gujarat Vigyan Sammelan. We are honored to have with us Dr. Vidyadhar Vaidya, National Governing Council member, Vigyan Bharati, VIBHA and former President, Vigyan Gurjari. Professor Rahul S. Kundu, Professor, Department of Biosciences and Member Board of Management, Saurashtra University, Rajkot. We are extremely grateful to our patrons and co-patrons, Professor Nilambari Dave Ma'am, Honorable Vice Chancellor, Saurashtra University, Professor Chaitanya Joshi, President, Vigyan Gurjari, Gujarat Prant, Dr. Narottam Sahu, Honorable Advisor and Member, Secretary at GUJCOST, Gandhinagar, Dr. R.G. Parmar, Registrar, Saurashtra University. I heartily welcome our today's invited speakers, Dr. Dheeraj Kumar Singh, Associate Professor, School of Nanosciences, Central University of Gujarat, Gandhinagar. Dr. Satyabrata Mohapatra, Associate Professor, Nanoscience and Technology, Head Multifunctional Nanomaterials Lab, Guru Gobind Singh, Indraprasth University, New Delhi. I also welcome Professor Nikesh Shah, Head of Department of Physics, Saurashtra University, Professor P.N. Joshi, Secretary Vigyan Gurjari, Saurashtra Prant, Rajkot, Dr. Puneet Negi, Assistant Professor and Head Department of Physics, Akal College of Basic Sciences, Eternal University, Baru Sahib, Sirmur, Himachal Pradesh. Dr. Ashwini D. Joshi, Assistant Professor at Department of Nanoscience and Advanced Materials, Saurashtra University, Rajkot. Dr. Piyush S. Solanki, Assistant Professor, Department of Physics, Saurashtra University. Dr. David Dhruv, Assistant Professor, Department of Physics, Saurashtra University. Dr. Megha Wagadia, Assistant Professor, Department of Physics, Saurashtra University. Moving ahead, I request my fellow researcher, Mr. Nisarg Rawal, to welcome and introduce us to our today's guest.
Thank you. It is my honor to introduce today's special guests, Dr. Vidyadhar Vaidya sir and Professor Rahul Kundu sir. Dr. Vidyadhar Vaidya sir is the National Governing Council member of Vigyan Bharati and former Prant President of Vigyan Gurjari, Gujarat Prant. Sir is presently affiliated to Department of Agriculture Meteorology at Anand Agriculture University. So I would like to invite Dr. Vidyadhar Vaidya sir to give blissful words. Over to you, sir.
How much time I have? Fine. So, welcome to all to this fantastic event, Vigyan Yatra, which is organized by Department of Physics, Saurashtra University, GUJCOST, and of course, Gujarat State Unit of Vigyan Bharati, that is Vigyan Gurjari. I am very pleased to participate in this event. Since 2009, I am associated with Vigyan Gurjari as the organizing secretary. Then from 16 to 20, I was the Gujarat State President, and now I am NGC member. So it is my pleasure to talk before you about small introduction about Vigyan Bharati. The Vigyan Bharati is a Swadeshi science movement of Bharat, which was started near Nagpur, 20 and 21st October 1991. The idea behind starting Vigyan Bharati is to highlight the contribution of Indian scientists or Swadeshi Vigyan, that is Indian sciences or Swadeshi Vigyan, and science which is propagated and by their own wisdom, they have progressed in the science. All those Indian scientists, we have to remember them. We have to remember their contribution. Just now, I am looking at one of the slides that Professor C.V. Raman, on whose discovery celebrate every year National Science Day. So, like that, there are several scientists who contributed a lot in the development of this science. Not only this, from ancient times also, many Rishi, Muni, they have contributed in various fields of science by writing the treaties. They must have conducted several experiments to come to the conclusion, and they wrote their uh, books in Sanskrit. Now, whatever available material is there, from that, it is evident that there is a lot of evidence of modern science. और जिसको हम बीज कहते हैं, ऐसे बीज उसमें हमको मिलते हैं. फॉर एग्जाम्पल द इन्वेंशन ऑफ जीरो, देन लॉ ऑफ right angle, that is Pythagorean theorem, and several Bodan concepts, it is also there. The various structures like Yajna Kunda, they were totally based on geometric figures or geometric precision was there in developing that. And big structures, big temples, then non-rusting iron pillar. There are several examples of it. And I am a student of meteorology, so I am also studying the ancient science of weather forecasting. And fortunately, I could do my PhD in the same subject in the year 2020. And I worked exhaustively on the hypothesis put up by Varhami in Gujarat. So in Gujarat, I have tested his hypothesis in seasonal rainfall prediction also, and dry spell, wet spell, the highest rainfall, the start of rainy season, end of rainy season, various planetary combinations. So all that we could do because of their voluminous work, and we can refer in today's language or today's scientific development. If we validate them, it is still useful. That is one of my conclusions in my thesis. So from that point, Vigyan Bharati is propagating the Swadeshi Vigyan and science which is developed or is being developed under the Indian scientific fraternity, that we want to highlight. So in a nutshell, we can say from Karnak to Kala, that is our journey. And Swadeshi Vigyan we are highlighting in the year of independence, 76th year. That is our what jubilee we can say, a platinum jubilee. So 75 years we are celebrating the Indian independence, and as per the wisdom or word given by Honorable Prime Minister Narendra Modi, this is Amrutkal from 2022 to 2047. In coming 25 years, we have to work hard. We have to start our progress in all realms of life so that we become Vishwaguru, developed nation, we can say. Economy-wise, science and technology-wise, and also culture. We got lot of cultural heritage from thousands of years ago. We have to preserve them. We have to sustain them. And in the light of our wisdom, we have to develop our country in coming for 25 days. This year, the theme is indigenous technology for Vikshit Bharat, science testing. In one of my invited talk in AIT College in Anand, I have said also. So from that, it is evident that patent-wise, research publication-wise, also R&D institution-wise or R&D manpower-wise, we are progressing leap and bounds. And we are coming to first 3 or 5 countries where science and technology can be developed in a perfect way. And ISRO is one of the prominent example of that, that we have successfully landed on the southern pole of moon in Chandrayaan-3. Also, there was a Mangal mission, Mangalyaan, we successfully completed that. Also, largest number of satellites in a on one rocket, we took them into the orbit. So that kind of world record we have already done. So from ISRO's example, or there are several examples. Various technologies developed by CSIR, if you see the list, we have progressed in various areas. Also, vaccine development. In Corona, we have developed 2 or 3 vaccines, and that was successfully implemented in our country. And also, we have given it to more than 100 countries in the world. So, Vasudhaiva Kutumbakam is also our theme. So, in short, we can say Vigyan Bharati is supporting that, and Gujarat with of Vigyan Bharati, Vigyan Gurjari is every day it is progressing to a very organization in a number and activities. Last time only we have put a world record, largest number of lectures in one single day. On 10th August, we have completed 361 lectures at different colleges, different speakers were there. More than 30,000 students participated in it. So likewise, this Gujarat Vigyan Sammelan is also going on successfully. This is the third version, and I wish great success to the team of Vigyan Yatra in Saurashtra University and other scientific to great success to this trip. And I wish best of luck. Jai Jai Garvi Gujarat, Bharat Mata Ki Jai. Thank you.
Thank you, sir, for your kind words. Now, I would like to introduce our today's next special guest, Professor Rahul Kundu, sir. Professor Rahul Kundu, sir, is from Department of Bioscience, Saurashtra University, and he is also the member of Board of Management of Saurashtra University. Sir has research specialization in marine ecology, ecotoxicology, and physiology. Sir has guided more than 75 MSc projects and around 25 MPhil students and more than 25 PhD students. Sir has also guided postdoctoral students. Sir has almost 110 publications in national and international journals. Sir has achieved various international awards and also worked on more than 10 funded research projects. Sir possesses many international collaborations and recognitions. So I would like to invite Professor Rahul Kundu, sir, to give their kind words.
Thank you, and thank you for inviting me and making me a part of Vigyan Yatra. जैसा मैं पहले बोल रहा था उधर कि I was actually working in the ecology. The department, our whole department is working on the marine ecology. Some people are working on the microbial ecology, some people are botanical, that is plant ecology, of marine aspects, and I am doing on the geological aspects. I am a geologist. So it's a long story, but what we are doing is that ecosystems, different ecosystems in the coastal areas, and monitoring their biomes, the different microbial populations working there in different areas, and plant algae, and of course the animals there. What we are doing at present is that surveying the entire coastal area of India, right from the Dwarka to Sundarban in West Bengal. And we are actually taking some niche area, say for example Gulf of Kutch, Gulf of Khambat, South Saurashtra coastline, then Goa coastline, the rocky coastal areas. And this is available in the western coast of India. But in the east coast, it is we are very much interested in Chilka Lake of Odisha. That's a unique ecosystem, and the biological diversity is different than that of the rest of the Indian coastline. So as I was talking to you earlier, that how to mix the different kinds of sciences there. It is interdisciplinary now. So in ecosystem, it is the modeling, the mathematical modeling, the physics modeling. When physics plays a role there, that is the force that come in with the tidal forces and how that is making the different ecosystems there in the coastal region. So these are the things. But basically today I am here to listen to Dr. Singh. So give me the opportunity to listen to him first. Thank you so much. Thank you. Over to you.
Thank you, sir, for sharing your knowledge and blessings with us. Now, I am fortunate enough to introduce our today's chairperson of the today's technical session, Dr. Puneet Negi, sir. So, Puneet Negi, sir, is assistant professor from Department of Physics at Akal College of Basic Sciences, Eternal University, Himachal Pradesh. The area of research, sir, is material science, nanoscience, nanotechnology, solar photovoltaic, solar thermal technology, etc. Sir has more than 12 years of research experience. Sir has guided 3 PhD students and around 11 MSc students for the projects. Sir has published 1 patent and almost 40 research articles in reputed journals. Sir has actively participated in many events, workshops, conferences, etc. Sir has also awarded the Meritorious Teacher Award for year 2020 during the 8th convocation of Eternal University, Baru Sahib. So, I request Puneet sir to please chair today's technical session. Over to you, sir.
Thank you very much. Good afternoon to everyone. And I would like to thanks to the Department of Physics, Saurashtra University, RAJKOT, for inviting me to session the chair. I'd like to thanks to Piyush Solanki sir. That actually he called me and I just got that such type of events is going on, and this is actually Gujarat Vigyan Sammelan 2024, and it's very nice to see such type of events that is organizing by the Department of Physics. It is Vigyan Yatra, a travel for scientific Indian minds towards the Vikshit Bharat, and it is very nice concept for such to organize such type of events. Uh, this is very insightful for the young minds, definitely, and us also, because we are continuously learning from each other in the research field. So it is very delightful for me that being the part of this event. So as this in this session we have, I come to know that we have the two lectures. One is from Dr. Professor Dheeraj Kumar Singh from Central University, Gujarat, and one is from yes.
Dheeraj.
Okay. Sorry. Dr. Dheeraj Singh, Dheeraj Kumar Singh. Okay, sorry. And next is Dr. Satyavrat Mohapatra. He's from Indraprastha University, New Delhi. So I would like to first introduce our first eminent speaker, Professor Dr. Dheeraj Kumar Singh from Central University of Gujarat. I just brief his introduction. He did his PhD from Bhu Varanasi at 2010. He did postdoc from NCL Pune from 2011 to 2013, from CSIR Nehru postdoc as a postdoc fellowship. He also did postdoc from South Korea, Seoul from 2013 to 2015, and also from University of Bremen, Germany from 2015 to 2016. He served as assistant professor in physics from 2016 to 2023 at IIT RAM Ahmedabad, and presently he is associate professor at School of Nanoscience, Central University of Gujarat. He is awarded as Alexandra von Humboldt Fellowship from Germany. He also as a JSPS Fellow from Japan. He also received Dr. DS Kothari Postdoc Fellowship from UGC India. Research Fellowship in Science from meritorious students, CSIR Nehru Postdoc Fellowship, CSIR SRF. He also completed various projects and got sanctioned from SERB DST, DST Inspire, UGC DAE CSR. Professor Singh guided 6 PhD students and 5 MSc and MTech students. His research area of interest includes functionalized nanomaterials, solar energy, frequency, and time domain spectroscopy, DFT calculations, ionic liquids, biomolecular, molecular interactions, etc. He has more than 80 publications. His H index is 26 and I10 index is 47. He published 4 Springer Nature books and 9 book chapters. He has 2 patents. One is USA and one is Indian patent. He organizes various conferences. And Professor Singh, also the Board of Studies member of Nanoscience, Saurashtra University, Board of Science, Physics, Dr. Subhas University. He examines various research theses from BARC, DU, Germany, etc. And he reviewed more than 100 papers like Applied Material Surfaces, Journal of Molecular Liquids, Vibrational Spectroscopy, Chemical Physics, etc. Dr. Singh is lifetime members of various scientific societies, LASSI, MRSI, EMSI, ISAMP, KCS, etc. So I would like to invite our eminent speaker, Professor Dr. Dheeraj Kumar Singh, on the topic of saga and development of Raman spectroscopy, role in Bharat developments. Sir, please grace us with your insightful words. Please, sir.
Thank you, Dr. Negi, for the detailed introduction. Am I audible?
Yes, sir. Yes, sir.
Okay, my screen is visible?
Fine, fine, sir. It's fine. Just make it as presentation mode, sir.
Okay. It's okay.
Fine, sir.
Okay, thank you, Dr. Negi, for the nice introduction. And first of all, I would like to thank the organizing committee, especially Professor Nikesh Sir, Dr. David, and Dr. Piyush Solanki for invited me in this very prestigious gathering of Gujarat Vigyan Sammelan by Dr. Nikesh Shah and the team at the Saurashtra University Department of Physics. Now I'm going to discuss about the saga and development of Raman spectroscopy and their role in Bharat development. I have divided my presentation in 7 distinct points. First of all, I would describe about the historical development of Raman spectroscopy. And I will describe why Raman spectroscopy is so important. And I will also start to describe the Raman effect on the basis of classical theory in physics and why this theory was failed to screen the Raman effect. After that, I would like to describe Raman effect on the basis of quantum physics, that is why classical theory was failed. And Raman spectroscopy basically depends on 3 different parameters: frequency shift, line width changes, and relative intensity. Actually, on these 3 parameters, all the information we can collect from the Raman spectrum. I will describe the detail about the frequency, line width, and relative intensity and correlate with their structure. Moreover, nowadays more than 25 variants of Raman spectroscopy has been developed. Most of the important Raman spectroscopy techniques are resonance, surface enhanced Raman, tip enhancement, and coherent anti-Stokes Raman spectroscopy will be covered during my presentation. Also, I would like to describe the application of advanced material, just like field Raman spectroscopy is a non-invasive and non-destructive technique for real-time monitoring of the biological sample. Application to molecular interaction, like 2 molecular interaction, hydrogen bond interaction, how we can predict that structural information from the Raman spectrum. Carbon-based nanomaterial, how they can characterize by the Raman spectroscopy, like D band, G band, what is the meaning? D and G band originated in carbon-based nanomaterial like fullerene, graphene, and carbon nanotube. Also, in forensic sciences, how the Raman spectroscopy are helpful to solve the criminal scenes. We will discuss by this Raman spectroscopy. Also, in food sciences, how the contaminations or impurity in our food items can be identified by Raman spectroscopy. It can be discussed. Further, nanotechnology used as a Raman technology known as surface enhanced Raman, SERS, as a sensor we will also discuss in order to sense the explosive material like TNT, RDX, and other explosive material. Moreover, nuclear material, nuclear waste items like uranium oxide, uranium will be also detected by surface enhanced Raman spectroscopy, and it will be shown during my presentation. And in last, biomedical study of and possibilities of investigate COVID-19 virus by Raman spectroscopy will be also discussed. In the last, I will also describe how this Raman spectroscopy can be work as a portable Raman devices, and it will be help to various vision of government of India like Make in India and many more. So first of all, I would like to describe what is the spectroscopy. Spectroscopy means that if light interact with your molecules or material, this information can be known as a spectroscopy. Spectroscopy, simple word, means light matter interaction. And now light contains every information about your molecules and material, either by absorption, either by scattering, either by fluorescence, either by transmit from the sample. So now, depending on this quality of the light, we define the spectroscopy. Suppose this is electromagnetic radiation, now incident on any molecules or material. If your your light is scattered from here, light is absorbed, we call it absorption spectroscopy. UV visible absorption spectroscopy are very helpful to understand this phenomena. And if your light is reflected, then reflectant transmission spectroscopy is there. And if your light is scattered from your molecules or material, we call it Raman scattering. And this Raman scattering can be three types: elastic scattering or inelastic scattering. Inelastic scattering can be two types: Stokes and anti-Stokes. We will discuss in later. According to energy of electromagnetic radiation, the various spectroscopy can be designed. We can see that from the lowest frequency as a radio wave. If you apply the radio wave on your molecule or molecular system, now it will give the information about the spin orientation in magnetic field, and the spectroscopic technique is NMR, nuclear magnetic resonance. If we are using microwave radiation on your molecular rotation, electron spin resonance will be helpful to giving the information about the molecular rotation, where microwave spectroscopy are very popular and helpful for the aerospace molecule characterization. Now, in molecular vibration, you know that every molecule are connected by atomic bond. In every material, every molecules are made by atom, and atoms are connected by molecular by atom vibration, covalent bond or single bond. So now this atomic vibrations can be characterized by IR light or Raman. So we can see that there is a light region that is known as IR region, near IR, mid IR, far IR region. There are three regions collectively known as IR region. When we apply any light in this region on any molecule, that is sensitive to molecular vibration, and it giving the information about the molecular structure in terms of molecular vibration. Also, Raman and IR both are giving similar information. That's why Raman spectroscopy also called in this region. That is mid IR region or more fundamental region of your Raman spectrum. It means any visible light, any ultraviolet light, or any source of light, if you are incident on any molecular material, the scattered radiation giving the Raman scattering. But this region fundamental mode are coming 200 to 4000 centimeter in frequency range. Now, visible range, UV range, X-ray in high frequency of radiation, gamma ray is actually very popular for nuclear related research. And X-ray light, actually we know that XPS, X-ray photoelectron spectroscopy are developed when we apply the X-ray light to any molecule. So we are interested only in this region where molecular vibrations giving information about the systemic molecular structure. So Raman spectroscopy falls in this region. Whatever region you can remind, this is in the mid IR region. So now this molecular vibration can be characterized by various functional groups. Molecule can have CH group, NH group, OH, SH, CO, CN group, a lot of functional group will be there, and all these atomic vibrations are vibrating at picosecond order. And these vibrations actually have some definite frequency, and this frequency actually can be captured by Raman light or laser light in terms of Raman scattering. So various molecular vibrations can be happen. Like molecule can be vibrated, there are two types of vibration. We call it fundamental vibration and non-fundamental vibration. Fundamental vibration can come into two categories: stretching vibration and bending vibration. Stretching vibration means if you're like a rubber type vibration, there are some stretching vibrations in your molecule, and stretching vibration can be three types or two types: symmetric and anti-symmetric. Symmetric means both atoms are coming together during the vibration. Anti-symmetric means if one atom are coming close to the one atom and second one atom is going to far away from that atom, so we call it anti-symmetric. So all this frequency of vibrations have different frequency, and we are detecting all this frequency in Raman spectroscopy. Further, bending vibrations can be also found in out of plane bending or in plane bending, and out of plane bending can be also characterized in terms of wagging or twisting. Twisting types of force are looking, we call it out of plane of particular vibrational mode. In plane bending, that is scissoring or rocking type vibration, we call it in plane bending. And we are not interested right now today in non-fundamental vibration, because a part of this fundamental frequency, various overtone and conduction tone are also observed. Overtone means if any frequency are coming at 1600, it means that at most of the double of this frequency, some overtone of this band can be obtained. But due to very low intensity, we are not interested in that. So now we can see there are some presentation of Raman spectra. Before going to much more detail about the Raman, I want to show you very simplest example of water molecule. Any molecule can have 3n-5 or 3n-6 number of vibration present in your Raman and IR, because Raman and IR both are giving similar information, but there are certain difference between Raman and IR. I am not coming to that. Just like Professor Kundu is interested in biological sample, why Raman spectroscopy has a lot of application, because Raman spectroscopy will not interfere with water molecule. In one line, we can say water molecule cannot interfere with our Raman signal with our molecule. But in IR actually absorb water in more light. That's why in biological sample, where most of the biochemical reactions are happening in water environment, Raman spectroscopy is ideally suited to apply this technique, because most of the biological sample involve water environment. So now we can say that suppose we are talking about water, that is H2O. In H2O, there should be either 3n-5 or 3n-6 number of vibration. N is the number of atom. And for linear molecule, 3n-5 number of vibrations will be there according to degrees of freedom, or 3n-6 number of vibration will be for non-linear molecule. I am giving simplest example of suppose water, where 2 hydrogen, 1 oxygen are there. So this is non-linear molecule, so we have 3 into 3 minus 6 number of vibrations will be obtained. It means 9 minus 6, that is 3 vibrations will be obtained during the Raman spectra of water. And same vibration will be also obtained in the IR spectroscopy, but change in different intensity, because Raman spectroscopy gives similar information. Symmetric stretching are more Raman active, and anti-symmetric stretching are more IR active. Anyway, now this is the Raman spectrum of water molecule, where we can see that at 1650 centimeter inward, we are getting a small peak which are connected to OH bending mode. OHO bending mode, you can see that all this type of bending, we are getting the peak. And here symmetric OH stretching are coming at 3800, something like that, and anti-symmetric stretching have this. So means any water molecule, if you are taking Raman and IR, these three frequency are coming from OH bending, symmetric OH stretching, and anti-symmetric stretching frequency. And we can analyze all the data on terms of frequency, their line will change, and their intensity variation about the Raman spectrum. Other vibrations can be given. Mode of vibration, you can see that this is a symmetrical stretching vibration. This is anti-symmetric vibration. Third one is scissoring type vibration. This is rocking type vibration. This is wagging, and this is twisting. Every molecule actually vibrate in these types of at picosecond order. And we are getting actually information about Raman and IR of these types of vibration. Every peak, every frequency are corresponding to certain vibration, whatever we are getting that. And every frequency have characteristics of particular chemical bond. Like C double bond O stretching mode is there, almost the vibration peak are clear at 1670 centimeters. C triple bond N is there, it means that 2200, something like that, your vibration peak will be obtained. I can show you, suppose this is a pyrrole molecule. Pyrrole is a very simple molecule. That is a 5-member ring. I want to show, if I don't know it will running or not. Now I can show you. Now I can show you this is a pyrrole molecule. What is optimized? It is CH, and this is NH group. So now there is a ring breathing vibration. These ring breathing vibrations are coming at 1000 centimeter inward. And if you record the Raman spectra at these vibrations, because these vibrations are very sensitive in ring type vibration. So now when we record the Raman spectra, due to these vibrations, we are getting a Raman peak where we can see that this 1100 centimeter inward. Now in pyrrole, we can see that there is a another spectrum, that is NH stretching mode is there. NH stretching mode means that there is NH molecule. NH molecule that it is stretching at certain frequency. Now this NH frequency is larger than 1600 centimeter. So we can see that this molecule pyrrole have some certain vibration in NH region, NH stretching region. Only this NH bond are vibrating, and this due to these vibrations we are getting Raman peak at certain 3300 centimeter. Now, if you are going to interact any molecule with this pyrrole, so either your NH stretching vibration will be affected. So now, after changing this peak position, spectral parameter like peak position, line width, and intensity variation, we can analysis our Raman result. So now, after understanding these things, now we can analysis carbon nanomaterial, forensic science, a lot of biomolecular polymer molecule, biomolecule in the more detail. So now, before coming to our application part, now I would like to describe the historical development. Actually, in India, we celebrate Raman effect. We celebrate Science Day, National Science Day on 28th February because of the invention of the Raman effect. Because C.V. Raman invented this Raman effect in 1928 on 28th February. So now, due to this discovery, we celebrate National Science Day in India. Actually, idea came to his mind in 1921. In 1921, C.V. Raman visited UK in British Columbia Congress. He visited their conference. Actually, one day he discussed his research with three outstanding scientists in UK: J.J. Thomson, Rutherford, and Professor H. Bragg. And he discussed his idea of research on optics in the UK. And one day during his visit in 1921 to UK, during a sea voyage, that is a Mediterranean Sea, he visited in one evening, and he saw that blue color of the sky. He Raman looked the blue color of the sea was looking, and he thought that why it looked like blue color. So now he began to doubt, because before the Raman explanation, already Professor Rayleigh, who already got the Nobel Prize in 1904, he explained that the blue color of the sea is just the reflection of the sky. But Raman was not agreed this explanation of the relay, and he thinking about this direction to that. And after returning to back in India, he started to research a lot of research work in this direction, that is diffraction of molecular crystal from the light. And he discovered that sea scatters the light. Matlab, this light, blue color of sky, blue color of sea, is just scattering of the light from the sample, not just the reflection of the sky. Now, after returning back to India, he started a lot of series of work in this direction with his PhD student, Professor S. Krishnan. And now this journey to Europe actually changed the history of Indian physical science. Now he got the Nobel Prize, and on the occasion of he awarding the Hooke's Medal on the Royal Society of London, Sir C.V. Raman, Lord Rutherford, during 1871 to 1937, he said that Raman effect must rank among the best 3 or 4 discoveries in experimental physics in the last decade. And he has proved that an instrument of great power in study of theory of solid. And also, why Raman is so special? Because Raman actually giving the characteristics, or we can say chemical identification of the molecule. Suppose pyrrole or any molecule is there, pyridine is there, or every fingerprint of our Raman spectra are there, or fingerprint of any particular molecule are there. Every molecules have different own Raman spectrum. That's why Raman spectrum is giving the characteristic feature. Same way, if any molecule have C double bond O group, their frequency is clear. C triple bond N group is there, their frequency will be clear. Overall, in one word, we can say Raman spectroscopy give chemical identification through the chemical bond vibration. Now, you can see that by this diagram, by this PowerPoint, C.V. Raman was the first to recognize and demonstrate that energy of photon can undergo partial transformation within matter. It means light is coming to the matter. Now light is scattered from the sample. Now this light can contain information about your molecular system, either by frequency shift, means small modification in their frequency. I will describe it much more detail by some schematic diagram in the next slide. And before coming to the Raman effect, I would like to also discovery of Raman spectroscopy. And before the Raman, C.V. Raman described the Raman in 1928. Actually, in 1923, already inelastic light scattering was already predicted by Professor Schmeckel by theoretical way. He was also German scientist. Professor Schmeckel already saw that the theoretically inelastic scattering was possible. After that, in 1928, Landsberg and Mendelssohn also see unexpected frequency shift in scattering. 1928, C.V. Raman and Carey Station see the feeble fluorescence from the neat solvent. In 1930, C.V. Raman won the Nobel Prize. After that, actually in 1930 until 1930, C.V. Raman used the mercury arc lamp to record the Raman spectrum of the sample. Suppose he has recorded benzene spectrum, but he has used mercury arc lamp and scattered light they have recorded. But now the discovery of laser in 1961 now revolutionized the field of Raman experiment, because laser have a definite property, that is monochromatic, high directional and coherent. And now laser light actually are frequently used, and it will revolutionize the field of Raman spectrometer. Further, in 1977, surface enhanced Raman, where your Raman is a very weak signal, but in the presence of metal nanoparticle or nanoparticle, your signal of Raman can be enhanced up to 10 power 12 times. Further, single molecule search is also possible. Nowadays, by combining the effect of surface enhanced Raman scattering along with scanning tunneling microscope, because scanning tunneling microscope, we know that quantum tunneling effect, scanning tunneling microscope give the atomic space information in microscopic image. But now STM along with SCRS, surface enhanced Raman, now giving the single molecular detection known as tip enhancement Raman. So now Raman spectroscopy is not only applicable for physics, chemistry, even material science, medical science, tissue engineering, even all material sciences, all sciences branch, engineering branches, they have applicable. And it is giving a lot of information. Few of them I am going to explain today. Like it is giving the information, fundamental information like chemical reactions parameter, like femtosecond order, picosecond order analysis. Single molecule or trace gas or explosive element. If there is a 1 point dust particle analysis, we can also do by this thing. Trace analysis can be also done by this thing. Carbon nanotube based material like graphene, fluorine, carbon nanotube can be ideally characterized by Raman spectroscopy. Other DNA, protein, folding of DNA, a lot of parameters can be described by this thing. Analysis of cancer, virus, other diseases can be explained by the Raman spectroscopy. Now I am coming very basic part. What is the Raman effect? Raman is an inelastic scattering of photon by a molecule. Suppose this is our molecules or material. Now, if a frequency of photon, suppose in photon in terms of laser or any light, suppose this frequency have h cut omega or h mu, this both are similar word. If h cut omega, this energy of photon is incident on any molecular system, then what happens? If scattered photon have same frequency as the incident photon, we call it relay scattering. It was already known before 1921. Now, Raman had added 2 more physical phenomena in this experiment. Then Raman has found that scattered photon, if have less energy than incident photon, we can this red one have less energy than incident photon, we call it Stokes process. Means energy, we can see that what energy was incident, it was h cut omega L, but now energy is decreased in terms of h cut omega minus omega. Means that now laser have transferred some energy to your molecular system. Now if you scattered radiation have larger energy than incident photon, means you can see that h omega plus omega 1, we call it just opposite of Stokes as anti-Stokes process. So finding of this Stokes line and anti-Stokes lines is known as Raman effect. Raman have simply given Stokes name because in fluorescence spectroscopy, if you know that if we excite any molecule by certain frequency, then emission wavelength was at lower frequency. That shifting from the excitation wavelength to emission wavelength is known as Stokes process. Due to that name, because of lowering of that frequency, Raman has given the name of low frequency Stokes process. Now Stokes and anti-Stokes both are equally spaced from the relay line. And we know that only 1 photon is scattered out of 10 million photon. Overall meaning is that Raman is a very weak process, and that's why in further I will also describe surface enhanced Raman spectroscopy in the presence of nanoparticle. But right now I am going to explain simply Raman effect. So finding of this Stokes and anti-Stokes actually known as a Raman effect. Now most of the Raman spectra actually recorded on Raman process, Stokes side. Because whatever Raman spectra we are seeing in the paper manuscript, we can see that that is a Raman shift is known as stroke shift. But they have not mentioned stroke because it is more common. Because most of the Raman is regarded stroke side because intensity of stroke side is much larger than anti-stroke side. But frequency is less, but intensity is larger. That's why we are recorded Raman in stroke side. Before coming to the quantum description, actually classical theory of physics also explained the Raman effect, but it was failed because according to classical, there are certain contradictory information from these things. So I want to show you very quickly. Suppose any molecule or material is irradiated by any electromagnetic radiation and induce radiation electric field E induce an electric dipole in your material. So P can be equal to alpha E. And E is the electric field, and this alpha is the polarizability which can oscillate at alpha 0, del alpha upon del Q, where Q is the coordinate change in your molecular system during the vibration. And electric energy can be also electric field can be oscillate at E equal to E0 cos omega t, and Q also oscillate at natural vibration frequency in terms of Q0 cos omega t. Now, when we put all this value E, Q, and alpha in this equation, in first equation, P is equal to alpha 0, and if you calculate this thing, then we are getting here value at omega 0 plus omega v blue color, omega 0 minus omega b is a red color. So according to this, induced dipole moment has frequency component, and we can see that omega 0 t is corresponding to relay scattering, and omega 0 plus omega b is corresponding to anti-stroke frequency, which have larger frequency, and the red one omega 0 minus omega v, it is corresponding to stroke process. So means overall, classical theory successfully explain the possibility of finding out relay line, Stokes line, anti-Stokes line. But here, classical theory failed to explain the unequal intensity of Stokes and anti-Stokes. In actual, Stokes have larger intensity than anti-Stokes. But according to classical theory, because we can see that coefficient of these both terms are same, it means equal intensity should be there according to classical physics. But classical theory here failed to explain about this effect. Now, quantum physics of theory Raman spectra can be easily described. Suppose there are some vibrational mode of any molecular system. Suppose B is equal to 0 is the ground state of molecular vibration, B is equal to 1 is the excited state. Suppose your molecule take energy from the photon, from the laser. Now your molecule go to the virtual energy state. This upper energy state in dot showing the virtual energy. Virtual energy actually it is not a real energy state, it is an imaginary state. Actually we assume that our molecule take energy from the light and it will go certain energy state in a virtual level. For suppose 10 minus 80 seconds, there are some regions of energy state are there. Now, if your spectral radiation are coming in same frequency, we call it B equal to, suppose molecule return back to B equal to 1 state, we call it relay scattering without changing any spectrum. But suppose your molecules take energy from photon and go to the virtual energy state after radiating energy, less energy than incident photon, like H cut omega 0 minus omega. We call it anti-Stokes line. And in anti-Stokes, few molecules are already in B equal to 1 excited state because due to some thermal fluctuation, few molecule can be already in excited state. And if molecule goes from this ground state or excited state to virtual state after radiating energy, larger energy than incident photon, we call it anti-Stokes. So now we can see that relay have 10 to the power minus 3 level intensity than laser light excitation wavelength. And now 10 minus 3 more lower intensity of Stokes side and anti-Stokes side are there from the relay. So means in experiment, actually by some nose filter and by some specific equipment purpose, actually we cut the signal from relay to anti-Stokes side. Actually we generally take the Raman spectra in this Stokes side because you can see the intensity of this Stokes side is larger than anti-Stokes. And because intensity is larger, because there is because ground state, here we can see that ground state population of molecule is much higher from the excited state. That's why Stokes have larger intensity because it's the transition takes from ground state to virtual state. So now we are interested in this thing. This is quantum physics description of the Raman spectrum. The first Raman spectrum built by C.V. Raman, it is given by this thing. At that time, as you know, laser was not invented. That's why they have used simple mercury arc lamp to record the Raman spectra from this. This is the first Raman spectra in terms of photographic plate using the benzene by the C.V. Raman. And what we do need to make a Raman measurement, not only Raman, in every experiment, we need a laser source or any source of the photon or light, and we can say one sample holder where we can put our sample either solid, liquid or gas. After that, from sample, now your light will be scattered. And now scattered light will go to the monochromator. Monochromator can be, nowadays people are using double monochromator like grating. Earlier, actually, Isaac Newton invented the laser spectroscopy where white light dispersed into 7 colors. It means that laser disperses white color in 7 parts. Now, same concept at the in terms of prism. Now the people are using grating where your scattered light will be tuned at different angle and different color. Now there will be some detector like charge coupled detector, CCD will be there to record your Raman signal, and through some software and computer you will record your spectra in terms of Raman. Now Raman has submitted their paper, only 2-page paper actually he submitted in Nature in 1928, and along with his PhD student K.S. Krishnan, the topic of his paper was a new type of secondary radiation, where he has also compared the results with some Compton corresponding to how because Compton is also saying the inelastic scattering of photon, but high frequency of photon actually will be there. So now in this only 2-page paper, actually that paper was published in Nature, and this title of this paper was a new type of secondary radiation, and this is detail of that particular thing. And now this is the experimental setup, whatever I have used during my Germany visit in lab of Professor Anup Materni and Professor Kiefer, where we can see that this is 90-degree scattering geometry. Now the geometry can be 2 types: 90-degree scattering geometry of Raman scattering signal and 180 scattering degree signal. So there are certain advantages and disadvantages. Now we can say that any laser of selected frequency like argon ion laser going to the prism selector. Suppose now 5.4 nanometer argon ion laser we are using. Now using the prism selector, we can cut the signal, whatever unwanted signal we can cut, and relay scattering filter, relay and anti-stroke lines will be cut from there, and only stroke line filter will do. And through the prism and rotator and through the lens, we are coming to the sample cell from there, photo lens to slit width, and it will go to the spectrometer where it will be showing the monochromator, and after that charge coupled detector will detect the signal through the computer. We are recording the Raman spectrum. This is the Renisha micro Raman setup where you can put the sample here, and Raman spectra can be recorded silently in terms of, and here 180-degree scattering geometry are there. And after getting the Raman spectra, actually we are getting 3 parameters: frequency, this is the x-axis data, we call it peak position or frequency, and intensity, and this at full width at half maxima showing the line width. Actually this any spectrum in terms of Raman, actually we analyzed all the results in terms of 3 parameters: frequency, line width, and intensity. And you know that frequency showing the static parameter like force, charge angle, binding, molecular interaction, all these things are denoted by frequency. Suppose 1500 frequency of any pure molecule is there, and if you mix it, any solvent or any molecule or any nanomaterial in that molecule, what happens, that vibration frequency can be either shift, either lower shift, red shift, either higher frequency shift, blue shift. So a part of that frequency shift, we can predict their structural information, how the interactions are possible between that. The line width showing the generally dynamic property. Dynamic property means how the molecules are dynamic in collision way, or what is the dynamic of vibrations in femtosecond level or picosecond level. Intensity variations, you know that transition probability means suppose your molecule going from one state to another transition state, your Raman spectroscopy clearly identified that transition probability in terms of intensity. Moreover, amount of material, how much amount or doping of material are present in your material, it can also be characterized by intensity variations in your. So means line shape analysis of this Raman spectrum, of any Raman spectrum, whatever you have recorded, any molecule, biomolecule, any material, explosive material, in terms of frequency, line width, intensity. So 3 parameters we are focused: wave number shift, line width change, intensity variation. We can see that. If your nature of interaction between 2 molecules is attractive, we call that frequency will be red shifted, means lower frequency. Like most strong hydrogen bonded between 2 molecules can be identified by red shifted hydrogen bond, means your frequency can be red shifted are blue shifted. And line width changes showing the dynamic property, where 2 types of dynamics can be related: population relaxation and vibration dephasing. Actually, we call it vibration dephasing is much more faster process than population relaxation. Vibration dephasing means if your vibration energy is reserved or relaxed, then in terms of only change in phase of your vibration can be changed, we call it vibration dephasing. Vibration dephasing is very fast process known as picosecond order. That's why vibration dephasing decides the line width of any Raman and IR signal. Means whatever line width we are getting, This is defined by the vibration dephasing. This is very fundamental principle. There are very much less time. That's why I am not going to much detail about that. Intensity variation, you can show that how much molecule associations are there. Suppose you have mixing 20% alcohol or 20% any solvent or 20% nanomaterial or doping and 80% doping, then it will be clearly identified by Raman by changing in their intensity. And we can predict that what is the changing in their Raman intensity and particular P. And in many molecular system where it is binding or which part of frequency are changing in their intensity, actually we can identify that what molecular interaction, which part of the molecular take place for binding or association of that. Overall, this parameter actually we connect structure spectra correlation. So now this spectra, Raman spectra and structure have direct correlation. Now application part, actually I am going to describe the application of Raman spectroscopy in 6 branches. First I will show you very small application of Raman spectroscopy in hydrogen bonding. Like if two molecules are interacting, how the Raman spectroscopy can able to describe their interaction. Ionic liquid water structure. Second, in carbonous material like graphene, quantum dot, fullerene, and any modification in carbon dot, how we can explain on the basis of Raman spectroscopy, I will explain. Now, food analysis, dairy, honest, any food material, how the analysis by the Raman spectroscopy, I will show. Now, forensic science, how the criminal scene can be explained on the basis of forensic science. We can also show the Raman spectroscopy usefulness in the forensic sciences in terms of anti-crime document, identification of any drugs, or detection of explosive material in any solvent in terms of dust type. The biological side like coronavirus, virus, diabetes, virus infections, how you can characterize by Raman spectroscopy, now I am going to describe. Now, environmental pollution like uranium or nuclear waste management, how you can characterize by Raman spectroscopy. All these 6 applications now I am planning to show you. Now in molecular interaction, suppose water, you know that water have a very strong absorption in IR region, which water have very strong results in Raman and IR. So hydrogen bonding, because water have liquid structure because of a strong hydrogen bond in water molecule. Otherwise, hydrogen bond without hydrogen bond, water would not exist in liquid form. Otherwise, it would be in gas form because hydrogen fluoride, HCl, actually everything is in gas form, but only water is liquid because of a strong hydrogen bond. The strong hydrogen bond or liquid structure we can characterize by Raman spectroscopy and IR. You can see that this Raman spectra of OS stretching mode. This is the this first spectra 3000 spectroscopy line curve fitting. It is giving a tetrahedral, and now this is a deformed tetrahedral. Now this is showing the 3 water and this is a single water. So this 2800 to 3800 centimeter inwards, we can characterize the water structure in terms of vibration peak. In any impurity in water, actually that frequency and that shape can be changed. So we can also analysis the presence of contamination of mercury sample in your water element by these 3 spectrum and parameter. Suppose I am going to give you a very simple example of spectra structure correlation, because without understanding the structure of any material, we cannot predict their property. That's why I am saying structure have direct connection to the property, and structure, molecular structure can be easily predicted by the Raman spectroscopy. I am going to give you simple example of Raman spectra of acetonitrile molecule, because acetonitrile molecule have a small component which have a lot of application in drugs molecule and biological molecule. So suppose CH3 C triple bond N. This is the acetonitrile molecule. You can see green part is carbon, white part is hydrogen, and blue part is nitrogen. So we are focusing this C triple bond N. Now, if you are going to record the Raman spectra of this pure acetonitrile, we have recorded on CN frequency at 2250 centimeter inward. So in Raman spectra, we are getting a Raman frequency of C triple bond N stretching at this frequency. Now, this is the pure acetonitrile. The first spectra, my cursor is open. Okay, now this is the upper spectra showing the Raman spectra of pure acetonitrile molecule. Now, after nonlinear curve fitting, we can find out there are 2 components. One component is small component, we are getting asymmetry is observed on the lower wave number. That is due to the dimer formation, means acetonitrile molecule also make a strong hydrogen bond with same molecule we call it dimer. So means dimer formations are easily observable in simple Raman spectra, pure acetonitride molecule. And this is isolated C triple bond spectrum. Means this spectrum are coming through the C triple bond and P. Now what happens? Suppose now we are going to mix 0.5 mole fraction or 50 mole fraction methanol or ethanol alcoholic solvent in this acetonitride. Let us see how the spectra structures are correlated. Now, if 50% methanol is mixing in this acetonitride, then what happens? The peak intensity of dimer will be break. That's why intensity of this dimer is decreased. And now a new peak is generated on the higher wave number side. You can see that on right hand side, that peak was not obtained in the pure acetonitride, but higher side, a peak is generated. We call it hydrogen bonded structure of acetonitride with methanol. If we predict Dept calculation theory, then we can see that this C triple bond are showing the dot 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 structure with HO. Means this C triple bond frequency now affected with these vibrations of the methanol. So now methanol make the strong hydrogen bond at CN. That's why CN frequency are changed in terms of new bondage. Now we have mixed 99% methanol solution and 1% is acetonitride molecule. Now we can see that dimer formation is very low, but now the intensity of these hydrogen bonded complexes is increased. Means that most strong hydrogen bonded are also affected due to the strong increasing the concentration of that. Means intensity variation you can see here right hand side in neat acetonide there is no any peak, but after mixing the ethanol there is a strong hydrogen bonded peak is coming, which are showing that without seeing the molecular structure we can predict that C triple bond N bind hydrogen bond to the methanol molecule, and this is clearly visible in that particular Raman spectrum. Also, when I was in South Korea, actually, I had published one paper in RSC Advances. That time, actually, one newspaper, actually, I read that DMSO is a very simple solvent, dimethyl sulfoxide. Dimethyl sulfoxide means there is CH3, S double bond O. Yellow one is sulfur and red one is oxygen. The SO is the most polar bond because Raman spectroscopy, people are more focused on the polar bond. So SO stretching mode, actually, in that media report, actually, I read that DMSO giving a magic bullet for the cancer treatment. That's why I am thinking that what happens in the magic bullet, why we are calling it magic bullet for the magic biological reaction. So because DMSO have a lot of biological reaction and medicinal property. That's why I have regarded this DMSO Raman spectra in pure form. So we can see that Raman spectra pure form in the bottom of the spectra are regarded, and there are 4 spectra are analyzed in terms of nonlinear coefficient. And now when we mix the water or methanol solvent in this DMSO, then we can see that here at the lower wave number there is no any peak in bottom up. But when we increase the concentration of methanol or ethanol solvent, a new peak is generated on the lower hand side, and the intensity of this newly developed band goes on increasing from down to upside. You can see that at maximum concentration or maximum dilution of DMSO with solution, we can see that. Okay, now Raman spectroscopy and short we can see also how the Raman spectroscopy can analyze for the forgery in your sample. Now Raman spectra pure pearl sample are there. Now Raman spectra of false pearl are there. So you can see that if Raman spectra of pure pearl is not directly matched to this false pearl, then we can identify the forgery are happened in the pearl. Because Raman spectra also giving the clear identification of the pure sample and mixing sample. And any fingerprint of any molecule, any fingerprint of our every different person have given different spectrum. Like our fingerprint spectrum are different and every print. So that's why this Raman spectrum of fingerprint can identify the forensic science information, or in order to solve the criminal science scene, Raman spectroscopy also very important. And more than 25 variants are Raman spectroscopy has been developed. So now I am going to more than 25 variants. I am going to describe Raman, resonance, surface enhanced, and coherent anti-stroke. Now I am coming to application of Raman to carbon-based material. How much time is there? Accordingly I can proceed because still I have more slide. Anyone confirm how much time I can give?
It's 10 minutes, sir. 10 minutes. 5 for
minutes.
discussion after that.
Okay,
Yes, sir.
Okay. I request to 15 minutes. Okay, 15 minutes I will try. Now, carbon-based material, we can say carbon is one of the most abundant element in the universe, and you know that a part of the graphite and diamond, now the discovery of carbon nanotube, fullerene and graphene make a new dimension in the carbon science. And now Raman spectroscopy is ideally suited technology to discuss this carbon-based nanomaterial, because carbon-based nanomaterial like graphene, fullerene, and carbon nanotube have a lot of application in strong, lightweight, thermal conductivity, high physical strength, narrow aerospace, defense, automotive things. So now carbon-based nanomaterials can be easily characterized by Raman by like graphite. That is the bulk level of the carbon. Now single layer of this graphite is known as graphene. Means by certain route, bottom up or top down approach, you can synthesize the graphene in single form. So graphene is nothing, it is just single layer of this graphite, which call is 2D material. Now if you fold this graphene in nano form, cylindrical form, we call it carbon nanotube, which are one-dimensional material. Now zero-dimensional material is fullerene also there. Now due to this CC bond, vibration, because CC bond have some stretching vibration, that's why Raman, because sp2 vibration, sp2 hybridization is there in sp2 hybridization is there in carbon-based CC stretching mode, and this sp2 hybridization can be easily detected by the Raman spectroscopy. Now I am showing the Raman spectra of graphene and graphite. Now suppose this is the Raman spectra of pure graphite and Raman spectra of graphene. How Raman spectroscopy identify the graphene? In graphene, actually we found a peak, we call it G band. G band means graphene band are in plane CC stretching mode. In plane band vibration, we call it G band. If you are getting a peak at 1589, we call it graphene band. And now we can see that how the Raman spectra clearly identify the graphite and graphene either by these two things. Now graphite, there are certain doublet is there, but in graphene only one single piece are there. Now in this spectra, we can see that this is the Raman spectra of graphite, but the Raman spectra of 1 layer, 2 layer, 3 layer graphene, we can see that it is a red shifted, because you know red shifted means that frequency is changing. So any defect, now we are interested to make a defect in any defects in your sample can give a extra peak as known as D band. D band matlab disorder or defect band. Suppose this graphene is single seed of graphite. Now if you are fold any small folding in graphene, means you are going to deviate your sp2 hybridization in sp3 hybridization. Any deviation in terms of any D band peaks will be observed in your system at 1300, something like that peak. So defects are disorder induced Raman band. D and D dash band are coming at 1350 and 1620 centimeter. So D band is located almost half of the position. Now you can see the Raman spectra of graphene oxide. Now suppose this is the monolayer graphene, and now graphene oxide. Because graphene is there, now graphene oxide means now we have deliberately make a oxidation in your sample of graphene. So now how Raman spectroscopy can be ideally detect these changes? You can see that here in pure monolayer graphene only G band in plane bending vibration or G plane bending vibration peaks are observed. But when you have make it oxidation in your sample, we call it graphene oxide. Now you can see that any deviation from honeycomb lattice means now disorder or D peak will be introduced in this. A new peak is generated at 1270 almost centimeter inward. This obtained of this new peak is clearly identification of your D peak or graphene oxide. Now also you can compare the graphene oxide, graphite and reduced graphene oxide. So now this comparison, by this comparison you can successfully characterize your carbon-based nanomaterial in terms of this. Also Raman spectra of carbon nanotube, because you know that carbon nanotube is just make the graphene in terms of cylindrical shape. Now it means that now we are getting a radial breathing mode. Radial breathing mode, if you remember, I have presented pyrrole ring vibration. Similar way, radial breathing mode type of vibrations will be introduced at this particular thing. And we can calculate by this equation 224 upon dt plus A. By this vibration, you can calculate. Either it is single wall carbon nanotube or multi-wall carbon nanotube, we can calculate these things and you can find out also it is metallic component or semiconducting component, we can also calculate. Characteristics are like metallic or semiconductor or multi-wall carbon nanotube or single wall nanotube can be also characterized by Raman. Also there are certain changes in the wavelength of the laser light. If you change, then you can also characterize by it. Overall, multi-wall carbon nanotube, single wall carbon nanotube can be also identified by the Raman spectroscopy along with their metallic and non. Simple example of graphene quantum dot. This Raman spectra, we can see that graphene quantum dot in first molecule, we can see that there is CO2 H functionalization. Now in second spectrum, there is graphene quantum dot 2, we have written COS, means 2 carboxylate group we have functionalized. Now in third spectrum, third molecule system, now we have size of this quantum dot we have increased, and two functionalization of COO carboxylate group are happened. Now let us see what is the Raman spectra of the corresponding structure. The first spectrum, you can see that there is a graphene quantum dot 1, graphene quantum dot 2, graphene quantum dot 3. So what is the changes? You can see that intensity ratio of the D and G band is changed. Here second intensity is larger, but in case of here intensity is almost equal. So we can see that the ratio of the intensity can be changed. The ratio of the intensity clearly identifies that particular quantization. Now, quantization means that graphene quantum diatation with significant intensity variation in D and G band with size of graphene quantum dot we can characterize. And this is a graph actually whatever we have explained. Furthermore, we can also show that what happens if age was functionalized graphene quantum dot. Like suppose here we have functionalized this carboxylate group, OH group, OH group, COH group. Now the size of this molecule are increasing, and also in zigzag and armchair, because there are three types of quantum dot: armchair, zigzag, and chiral structure. So these types of structure can be also characterized by functionalization group. Like you can say D1, D2, D3. D3 means this systems can be characterized in terms of COH group, C double bond O group. So what types of functionalization you have used in your carbon-based material, it can be clearly identified by Raman spectroscopy. Further ratio of the I, D, and G band intensity variation you can identify. Recently, our group actually also performed detection of melamine. Melamine is a dangerous molecule which are very health concerns issues. We have detected melamine with a functionalized graphene quantum dot by thinking by where 736 peak used as a marker Raman band to identify these things. So now, moreover, nowadays 2D material in terms of diisocyanide, WS2 or MOS2, actually Raman spectroscopy can identify clear the number of layers. How many number of layers are there? Suppose simple one layer, bottom of spectra of Raman layer of WS2 nanoparticle are there. So one layer, you can see that intensity of this peak 345 peak is larger than second peak. But when number of layer is increasing from one layer to 4 layer, we can see that intensity is changed. Here, first intensity is now down, second intensity of the peak at 420 centimeter inverse is great. So means intensity variation actually give the clear identification of the number of layers present in nano level, where TAME actually will get some difficulty to identify this characterization. But Raman spectroscopy clearly identified the number of layers in your 2D material by certain peak vibration in. Also, now I am coming to application of Raman spectroscopy in forensic sciences. Now, Raman spectra are very applicable to calculate or very differentiate the two sample, like wet sample of and dry sample of. This you can see the Raman spectra wet blood sample and dry blood sample. By this two peak identification 1155, 1511. We can identify.
क्या ले जाना आप ले जाओ नोट करना नोट कर लेना.
Now you can see that these two peaks are actually showing the identification of wet and dry thing. Now we can see that human dry blood and dry human semen analysis can be also done by the Raman spectroscopy, where unique to only human semen, only this peak identification or observation of this peak at 2968 peak are generally unique identification of Raman marker band for the human semen. So once blood sample and dry sample, dry blood and dry sample of the semen can be also identified by Raman, which can be very helpful to help the verification of criminal scene. Now I am going to show you detection of fluoride nitride pen. This is a very dangerous chemical. Actually, people are used actually nowadays. Fluoride nitrogen is a well-known date-raping drug molecule. Actually, the criminal actually used to mix this chemical in the before do the date-raping drug molecule. People are using that criminal actually used in some types of rum, bacteria, water, or in vodka types of alcoholic solvent. Actually, Raman spectroscopy can easily identify it's very small amount of this chemicals can be, because this chemical is very colorless, odorless, and tasteless. So identification of this chemicals is not very straightforward in any molecules or in water, even water. But Raman spectroscopy clearly identifies their observation. So for forensic science actually also used to observe this data. You can see that this peak Bacardi rum, that is alcoholic solvent, Bacardi rum, pure fluorescent peak are there. In Bacardi rum, if you are changing the concentration, so we can found out alcoholic peak. Bacardi rum, there is no peak. But this peak at something like the 1370, this peak is observed in your solvent. That is a clear identification of this white Bacardi rum. And in Vodka also, this sticks up of rum. So means overall, certain peaks are clear identification of present of these types of chemical which are criminal actually used for the day trapping case. Also detection of explosive and clotting. Suppose terrorists are using many explosive element, TNT, RDX, and are many ammonium nitrate. These terrorists using the terrorist attack in the human civilization, and sometimes this small part post event of the terrorist attack, actually forensic team can collect the one sample data and they can collect the things, and by Raman spectroscopy it will be giving similar information about the identification of either it is RDX or TNT by identification of certain peak. And also food analysis, we can also compare the Raman spectra of milk brand like various pasteurized milk and lard fat and butter fat. In terms of protein, we can identify their identification in terms of peak. Now, surface enhanced Raman spectroscopy is very important because Raman is a very weak process. Only one photon is scattered out of 10 million photons. But in the presence of nanomaterial like metal nanoparticle, gold or silver, now signal of Raman spectroscopy can be enhanced. There are two types of enhancement: electromagnetic, chemical charge transfer enhancement. So electromagnetic chemical enhancement means that your Raman signal can be enhanced up to 10 to the power 12 times. It means that at least single molecular detection can be possible using the nanoparticle. So what happens if your explosive element like RDF or TNT are there in only 10 minus 12 mole or nanomolar concentration in any particular surface? Now you can make a nano substrate, nanometal substrate. Now you can put only one drop or one dust particle of TNT at that nano substrate. This nano substrate will enhance the signal of that particular molecule, and we can detect by certain peak will be observed, and we can detect that either it is TNT or RDX or RNT or another explosive element. So I am not coming to much more detail of surface enhancement mechanism. Just I want to show some peak because you can see that this is the application of surface enhanced Raman spectroscopy using metal nanoparticle. TNT, trinitrotoluene, this is structure of this is TNT. This is the RDX. RDX is also known as this molecule here. We have written RDX is known as some cycloprotein in molecule, and RDX structure is also very simple. And the contamination of this RDX or TNT in groundwater even are very dangerous. It is reason for anemia and abnormal liver function. Sometimes cancer risk are children in contamination in our body by certain. So now we can see that this RDX is known as cyclotrimethylamina-trimamine. So this RDX is a molecule, and molecule are their vibration. The identification of this RDX in one drop can be identified by Raman spectroscopy. So there are certain process of nanomolecule synthesis process where suppose this is a design of some AU gold TNP based surface substrate using some bottom up or top down approach. You can make some substrate of the nanoparticle. Now we can record it, and you can see that there is no any spectrum of Raman, but in the presence of this 6 microliter of 1 nanometer TNT solution, we are getting the spectrum. It means the signal is enhanced in the presence of that, and identification of this ABCD peak actually is the clarification of that thing. Now you can see that if TNT, TNB or DNT all are very similar types of explosive element used by terrorists, and it is easily detected by indifference by this thing. Principal component analysis actually clearly identified that there are 3 different peaks. So by Raman spectroscopy, we can also see the difference between RDX and this. So now we can see that RDX and TNT at lower difference means that if 10 minus 12 molar concentration, it means a small quantity of TNT RDX is dissolved in liquid phase. Then Raman spectra in terms of nanoparticle, we can find out their uptake. You can see that here from upper to lower side, if you are coming, means we are decreasing the concentration of this thing. Means 100 micromolar to 100 femtomolar. Means pico 10 minus 12 molar means a very small quantity of RDX is present in liquid phase, and their identification are coming in terms of some certain peak. So means Raman spectra in the terms of nanoparticle as a surface enhanced Raman spectroscopy easily detect the explosive element. A lot of explosive element actually can be detected using the Raman signal. We can see again TNT using a PABT. PABT is a gate Raman signal. You can see that this is a Raman signal of 10⁻7 molar PABT silver nanoparticle. There is no any signal. Red one, there is no any signal. But when we have added trinitrotoluene, that is explosive element with PABT sample with silver nanoparticle at silicon surface, at picomolar concentration, we are getting the Raman signal. The identification of this type of peak actually give the clear identification of TNT. Also, this is showing this peak is actually showing the femtomolar. There is a background correction and there is a femtosecond. Now I am coming nuclear waste. Nuclear waste means nuclear, VIBHA atomic research center or any country actually also.
Professor Singh.
Yes.
Sorry to interrupt you, sir.
Yes, 2 minutes. I am taking.
Sir, we are 5 minutes ahead actually with our time.
Okay.
Yes, sir. Please.
Okay, sir. Detection of nuclear material can be also, because nuclear element and nuclear weapons, actually people are using nuclear weapons for any country, and nuclear waste material can be also exist in our earth, and which can be detected by Raman signal. We can see that by this certain peak. Now, due to certain time, now I am coming. Actually, this work I have detected when I was working in South Korea. This work was detected site of cytidine and published in Journal of Hazardous Material. So now I am coming self-healing material. Actually, I want to Raman spectroscopy in medical application. I can show you Raman spectrum healthy and cancerous cell. Means if healthy cancerous cell can be clearly identified by the Raman cancerous cell by Raman certain peak. Suppose in Raman spectrum biomolecule, a lot of vibrational band are there. You can see that, and the corresponding origin of the molecule can be written here, like protein, lipid, protein 2, nucleic acid, and every peak are connected to that particular thing. So we can also identify the normal cancerous cell and cancerous cell, healthy cancerous cell and cell. So now this is the coherent anti-Stokes Raman. This is a very non-linear Raman technique. Actually, I am not coming to this part because this actually non-coherent anti-Stokes Raman is a very popular technique nowadays in order to understand their dynamics behavior of the molecule and material. So due to shortage of time, I am skipping this slide. CARS is very helpful to imaging the biological sample, lipid and something like that. Now, coronavirus also can be clearly characterized by the Raman spectrum, because in coronavirus you can see that there is S protein, E protein, glycoprotein, liver protein, and every protein is making by the molecule, and making molecule means there are certain molecular vibration, and it is easily characterized by various technique by Raman spectroscopy. Now, fastest CARS-based are actually we can. Suppose if you are using two types of viruses, now known as influenza virus H1N1 and CBV3 viruses, two viruses simultaneously we are using, then we are getting the peak. This blue types of peak are identification of H1N1, and here blue types of peak are identification of CB3B3 virus using the Raman spectroscopy based technology. And also recently virion based technology are developed where nanoparticle, nanorod are using to identify various types of viruses on that particular. So now, concluding remarks, Raman have a lot of application not only for molecule material in food science, carbon science, forensic science, explosive element, semiconductor industry, even all the way. So now Raman spectroscopy are very helpful for Atmanirbhar Bharat Abhiyan, because for base for any developing country part of the self-reliant Bharat, where economy, infrastructure, technology development, demography, demand and supply. So now our Raman spectroscopy can be also fulfill the mission of Make in India programs and Swachh Bharat mission Abhiyan by various characterization technique. Because in Make in India, now Raman got the Nobel Prize in India, but the production of Raman spectroscopy is very few in India. But by Make in India mission, nowadays people have started to make Raman spectrometer in India also, which is also a part of Make in India. A lot of instrument actually started CTR 300 by CSIR, MPRI. A lot of instrument have been. Nowadays people are also focused on this is an indigenous technology, Raman spectroscopy by motivation of Make in India, slogan by Government of India, Honorable Prime Minister Narendra Modi ji. Now you can see that a lot of portable devices are now people are making in order to characterize your sample of various things. Now a lot of actually renewable energy and semiconductor industry are also very focused time for our India. Our government are going to focus in solar cell industries, renewable energy, battery, hydrogen energy, where Raman spectroscopy are very important to characterize this system. And by focusing this technique, we will achieve our Vikshit Bharat Abhiyan in 2047 by which portable Raman spectroscopy. So this is the things, and here Raman spectroscopy can be applicable to semiconductor and solar energy industry, which can fulfill the Abhiyan of Make in India. So this is the recommendation of my recent book, Nanomaterial, and one more book is coming very soon. This is my collaborator. I would like to thank all my collaborator and PhD student, and some PPTs are also taken from my research group and internet. I would like to acknowledge. Thank you very much. And sorry for 10 minutes extra.
So thanks a lot for your presentation, sir. It was very informative for all, because you include all the history background of the Raman spectroscopy along with its wide applications. So thank you so much for this wonderful presentation, sir. So I would like to, if there are any question from the participants, please you can ask.
Hello, am I audible?
Yes, yes.
We will take only one or two the shortage of the time.
Sir,
please.
I'm Sam Khatri from Sardar Patel University. Sir,
I am also give my email address.
So, sir, actually, I'm working in the direction of metal oxides, and one of the Ag doping in my material shows photochromic effect. So, according to literature survey, it can be due to the conversion of metal to metal ion or metal ion to metal. So, can I understand that mechanism by Raman spectroscope?
Metal ion, actually, you know that metal actually bind at a very low frequency. Low frequency means suppose any binding of metal with molecule like nitrogen group are there, nitrogen bind with gold or silver. That frequency region is 100 to 200 frequency centimeter inward. So where it is very difficult to identify the binding of metal to any molecule. If metal is there, means their identification is low frequency. But in far IR spectroscopy, like far IR spectroscopy, we can very easily source that particular interaction of metal binding. Because generally we are focused in Raman spectroscopy fundamental mode from 200 to 4000 centimeter inward.
Yes, sir.
Any other query from the participant?
Hello. Hello.
Yes.
Sir, this is Ketan Navle from IIT Indore. My question is, somewhere in your slide you mentioned about higher order Raman modes.
Yes.
So what is the meaning of this higher order Raman vibrations?
Higher order non-linear Raman, whatever you are talking about, non-linear Raman mode or?
Yes, higher order non-linear Raman modes.
Non-linear Raman means that, because we have discussed so far linear Raman. Linear Raman means when induced dipole moment P is directly proportional to first power of polarizability, means P is equal to alpha E. But you know that your electromagnetic radiation can also interact, means molecular vibrations of your molecule can also interact with second harmonic vibrations or more higher power of electric field. Like P is equal to alpha E plus alpha 2 e to the power 2 plus alpha 3 e to the power 3. If second harmonic generations are also involved to interact with molecular vibration, we call it non-linear Raman effect. Where Raman spectroscopy and surface ion is linear Raman effect. But non-linear Raman effect, we are used like coherent anti-Stokes Raman. Actually, we use pulse laser light, where your means highest normal mode actually interact with your molecular vibration. So there we use two pulse laser pulse laser actually we use to pump your molecule and material in excited state, and now Stokes side Raman also used same time, and same time third laser pulse is used as a probe system. That's why we can generate the Kars pump, which is non-linear Raman. Because non-linear Raman have a lot of application. Like fluorescence will be quenched. In Kars there is no any fluorescence, and Kars is a non-linear Raman.
Okay. So actually I have one more question.
Yes.
The time. Actually, in some materials like in perovskite, ABO3 system,
Yes.
when we dope something at B site or A site, and
Yes.
that will have a change on the FWHM of the Raman peak. So is
Yeah.
it necessary that when doping at B site or A site, it will be always like the increase in FWHM will be there, or this is not the hard and fast rule that the FWHM increases with the doping?
No, actually, as you know that in XRD also broadening of the peak actually correlated with the doping strength and the doping material. How much doping you are going to give in your material, line width is changing. Also in Raman spectroscopy, line width give the dynamic property. Also not a doping property, not very much effective way, but property mean dynamic property of doping, how the molecular environment is changing. Line width can be there, but it is not necessary that always you are getting these types of broadening in your molecular spectrum. But molecular system, like your molecular system is there, so homogeneous broadening can be obtained. But in case of your perovskite, I don't think there is some significant broadening will be obtained. And you can be able to, but XRD can be easily show the dopable things of broadening.
Okay, thank you, sir.
So thanks, Professor Singh, for such a nice presentation. And if there is any question for the participants, they can ask to Professor Singh through mail IDs.
Yes, most welcome.
Thank you, sir. Thank you.
Thank you.
So now the times goes up to the second our eminent speakers, because we are late up to 15 minutes, and at 4 we have the second session. So I think we should start. So first of all, I would like to introduce our eminent speaker for this session. Dr. Satyavrat Mohapatra, Professor of Nanoscience, Nanotechnology at University School of Basic and Applied Sciences, Guru Gobind Singh, Indraprastha University, New Delhi. Sir, welcome to the session, second lecture of this session. So first of all, I would like to introduce our eminent speaker. Dr. Satyavrata Mohapatra is presently working as Associate Professor of Nanoscience and Nanotechnology at University School of Basic and Applied Sciences, Guru Gobind Singh, Indraprastha University, New Delhi, India. Professor Mohapatra obtained his PhD in Physics from Institute of Physics, Bhubaneswar. After completing postdoc from Inter-University Accelerator Center, he served as visiting scientist at Brain, Korea, from St. Suwan, South Korea, and visiting fellow from CSNSW, Orsay, France. He joined Guru Gobind Singh, Indraprastha University, New Delhi, India at 2008, where he is currently heading the Multifunctional Nanomaterials Laboratory and member of the Academic Council. Dr. Mohapatra is a member of the National Academy of Science, India. His excellent research credentials are reflected by his more than 140 peer-reviewed papers in international journals, one edited book, 2 book chapters, and over 110 papers published in international and national conferences. Dr. Mohapatra has been included in the world's top 2% scientists in applied sciences for the last 4 consecutive years, with best global ranking of 1,397, and is ranked 29th among Indian scientists by Stanford University, USA. He is an editor of editor of Materials Open Association, and he's associate editor of Nanocatalysis, specifically section of Frontiers in Nanotechnology, associate editor of Nanoscience, section of Frontiers in Chemistry, topic editor of Emerging Leaders in Nanotechnology, topic editor of Spectroscopic Analysis of Nanostructured Systems in Chemistry, section editor of Current Nanotoxicity and Prevention, and editorial board member of international journals, recent patents in nanotechnology and general chemistry he has. He is a recipient of DST Young Scientist Award in 2008, Best Researcher in Science Award in 2014, Faculty Achievement Award in 2016, and Faculty Achievement Award in 2021 too, and has been included in top 10% highly cited authors in Royal Society of Chemistry physical portfolio journals. He has been working as a reviewer for over 100 international journals of repute. His research is focused on the development of multifunctional hybrid nanostructures, 2D materials, and metal oxide semiconductors based hybrid plasmonic nanostructures and nanocomposites, coatings, and their ion beam engineering for applications in catalysis, gas sensing, SERS, biosensing, antimicrobials, and water purification. So I would like to request to our eminent speaker on his talk on the topic ion beam engineering of nanostructured metal oxide thin films and plasmonic nanohybrids for enhanced gas sensing. Please, sir, uh, please start your topic and enlighten us of your words to us. Am I audible, sir?
Yes. Uh, yeah, at the outset, I would like to thank the organizers, Professor Nikesa and Dr. Pio Sulanki, for the invitation. And here I will be talking about. Is this visible to all of you?
Yes, sir. Yes, sir.
Not, yes, sir.
Okay. So I'll be talking on ion beam engineering of nanostructure metal oxide thin films and plasmonic nanohybrids for enhanced gas sensing. I am Satyabrat Mohapatra from Guru Gobind Singh Indraprasth University, Delhi. So I'll be talking about.
Sir, please make it in presentation mode, sir.
Okay, just a moment. Just a moment. Is this okay now? Yeah. So, I'll be just talking on metal oxide semiconductor-based gas sensors,
Yes.
tin oxide nanostructures for gas sensing, and then various approaches we have used to improve the gas sensing performance of tin oxide nanostructures like copper doped tin oxide nanosets, gold tin oxide plasmonic nanohybrids, and then we have used ion beam engineering of nanostructured films for enhanced carbon monoxide gas sensing. Health and safety issues associated with various toxic gases and contaminants has always been the subject of highest priority because it affects us. And there, this development of metal oxide semiconductor nanostructure based sensors, in particular gas sensors, have attracted significant attention. Simply because of their low cost, simplicity, compact, and very simple electronics. Now, these unique optical and electronic properties of metal oxide semiconductors, along with the ability to easily fabricate high surface to volume ratios nanostructures, makes them exciting candidates for applications in gas sensors. In particular, for practical applications, gas sensors should have high selectivity, high sensitivity, and small response time and recovery time. And these factors, these parameters, which lead to improved gas sensing performance, are affected by factors such as crystallite size, porosity, surface area, and presence of various catalysts. So the approach for achieving a very efficient gas sensing based on metal oxide, hence basically focuses on handling or engineering these parameters. And among metal oxide, tin oxide nanostructures are one of the most exciting materials for gas sensing applications, and because of their exciting electrical and optical properties. However, there are limitations such as poor selectivity, poor long-term stability, and of course, the elevated temperature of operation is one of the major concerns. And that's why it has attracted attention, and there have been several approaches to improve the gas sensor response of tin oxide nanostructures, employing approaches such as doping with various metals, such as copper silver. In this case, we'll be discussing decoration with noble metal nanostructures by creating various junctions, and of course, by using nanohybrids or nanocomposites with other semiconductors. And the ion irradiation as an alternative route to engineer these parameters, and hence the gas sensor response, considering the effective and ease with which one can engineer nanostructures using ion beam. So this is one of our works which was published in 2016 in PCCP, in which we dropped copper into tin oxide nanosheets prepared by a fissile wet chemical method, and we achieved excellent carbon monoxide gas sensing response. In this, the FESCM clearly shows that there are nanostructures. You can see that SC0 is the pristine tin oxide sample. This is prepared by wet chemical method, in which we went for stannic chloride, urea, and in the presence of CTAB as a surfactant. So now what we varied is the doping of copper inside the tin oxide, that's 0.5%, 1%, and 1.5%. And you can see the respective FESCM images are clearly seen, in which you can see this SC01 and SC02 shows distinct flake-like structures, and as you can see that they consist of nanosheets, which is clear in the TM image. So the TM image shown clearly displays that there are nanosheet-like structures, and the HRTM confirms that this is the tin oxide. This is 3.29 angstrom, 110 lattice planes clearly visible, and of course from the EDAX spectra again it confirms that these are copper doped tin oxide nanosheets. The XRD patterns confirm again the tetragonal tin oxide structure of these nanosheets, and the average crystallite size reduced from 16.1 to 11.5 nanometer upon copper doping. So there is a slight decrease in the crystallite size, and the lattice parameters varied from 4.714 angstrom and 3.179 angstrom to 4.73 and 3.156 angstrom upon copper doping. So there you see that there are changes in the lattice strain, and of course a variation or a decrease in the crystallite size on copper doping. The photoluminescence results shows peaks at 369, 392, 408, and 445 nanometer, and you can see that they have distinct emissions from the oxygen vacancies around 408 and 445 nanometer, and you can see that there is an enhancement in this defect luminescence upon copper doping, and the UV emission enhancement due to formation of nanosheets upon copper doping. And this is interesting. This is clearly seen in the Phy-SU images as well, where copper doping changes into more of nanosheets of structures. And that's where, so this will have impairing on the gas sensor response, because you need to have defects for efficient adsorption of the gas molecules. And these defect emissions are significantly enhanced, which is attributed to creation of defects in the form of oxygen vacuum.
Intensity versus wavelength UV.
Hello, am I audible?
Yes, sir, please.
Okay. And we then checked, see, two-dimensional structures are interesting, bit of any metal oxide, because of the inherent high surface area they offer, and plus, if you can tailor the defect concentration or the type of defects on these 2D structures, it makes them exciting materials. So this two-dimensional tin oxide nanostructures optimally copper doping can do some improvement in sensor response. That's what we wanted to check, and we went for carbon monoxide gas sensing. Carbon monoxide is one of the most lethal toxic gas which leads to a lot of death, and that's where it is important to develop sensors, efficient sensors, which can do which with a very strong what you call quick response and recovery time. And we see you can see that this sensors which are created out of this material showed an operating temperature which is slightly higher, 240 degrees centigrade. But on increase in this doping, you can see this SC02, that is 1% copper doping, leads to a maximum enhancement in the sensor response. And in B, you can see that this is basically the transient curve, which shows that during this gas in or gas out, how the resistance varies. It gives an insight into how this what you call response time in this case is basically you can see that this response and recovery time varies when we dope copper. So there is a significant decrease in the response response time and recovery time, which is required for gas sensing response. And another parameter, another sort of criteria which is important for deciding or developing a gas sensor is the selectivity. When you toss it against other gases, because you will not have only carbon monoxide, you have an array of gases. There it has to have selectivity for carbon monoxide. That's what is required. And you can see that in C, you can see the sensor response. There is a selective sensor response for carbon monoxide, which is the highest. Of course, there are interference with acetone, and but other gases you can see they're negligible. So this shows a good sort of selectivity. Of course, there can be improvement further, and that will show in the next studies that we go on reducing this operating temperature and improve the sensor response and decrease the response and recovery time. That's what is needed for development of a good or efficient carbon monoxide gas sensor. Now you can see this when you dope with the copper 0.5%, the response time itself decreases from 60 seconds to 18 seconds. Recovery time drops up from 90 to 23 seconds. You can see that they're pretty large as compared to, of course, as compared to other results, other studies that are reasonably good, but we want this response and recovery time to be as small as possible, because because if it is large, then you are exposed to that toxic carbon monoxide gas for that time. And in cases where there are workers, this leads to a lot of fatalities. And we want to minimize that. We want to come up with a sensor, efficient sensor, which can respond in seconds, just a few seconds. That's what the goal. And in this, you can see that 1% copper doping does achieve that 9 seconds and 11 seconds as recovery time, which is very, very good, considering that in few seconds you can sort of detect carbon monoxide, and hence there can be a mechanism where you can alarm goes off and people are evacuated quickly. And that is exciting. That is particularly of importance because it saves lives. Now, gas sensing studies, you can see that 1% copper doped tin oxide nanosheets is an exciting material, but you can see that the operating temperature got to be brought down from 240 degrees centigrade. And in this case, what we achieved that the enhanced carbon monoxide sensor response is basically a combined effect of reduced crystallite size, a nanosheet-like morphology with high surface area, and increased concentration of oxygen vacancies, which you achieve in this case. In another study, we wanted to explore that what happens if we make hybrids, plasmonic nanohybrids, gold tin oxide plasmonic nanohybrids that we need thin film coating. So for that, what we used is we coated 45 nanometer tin oxide films by thermal evaporation, and then we spotter coated 5 nanometer gold film onto them. These studies came in Applied Surface Science in 2020 and in JALCOM in 2016. So these are studies. These studies are from one of my PhD students, Neha Bharadwaj. Now, FESCM, you can see that this is a pristine tin oxide film, and then on coating, gold coating, you can see there's nanoparticles of gold decorating a tin oxide film surface, which is again clearly evident in case of AFM results in C and D, where the average size, nanoparticle size, is 13 nanometer in case of pure tin oxide, and is increases to 23 nanometer in case of gold on tin oxide. So to look further, we went for cross-sectional transmission electron microscopy, and they can see that in B you can see these particles of gold on a tin oxide film, and that we went for rigorous analysis with you can see that in EDAX and how the variations of tin, gold, and oxygen across this film. So it clearly shows that this is made up of this is a gold tin oxide hybrid film. And the average XRD again shows that we have orthorhombic tin oxide, and this crystallite size of this orthorhombic tin oxide varied from 21 to 22.7 nanometer, while that of gold nanoparticles decorating tin oxide film was only 6.8 nanometer. So in addition, you can see that because we went for carbothermal reduction as a technique, so there are additional peaks of tin and gold tin oxide, because the approach we wanted to go for is creating Schottky junctions. You know that in this case, these metal semiconductor junctions will be beneficial for improving the sensor response. That was basically the goal. Now, the optical absorption data again shows that we estimated band gap from this analysis. And in case of pure tin oxide is 3.45 electron volt, and in case of upon gold decoration, gold nanoparticle decoration, it's reduced to 3.04 electron volt. And this decrease in band gap on gold nanoparticle decoration is simply because of the increased electron concentration in the conduction band of tin oxide, which originates from the surface plasmon-driven electron injections into the conduction band. You know that. So it depends on the plasmonic nanostructures, how many you inject electrons into the conduction band, and this alters, and this is mainly responsible for this band gap reduction. This work was published in Applied Surface Science 3 years back. Now, what is important here, we wanted to see that whether gold nanoparticle decoration can improve the carbon monoxide gas sensing response. We are trying to explore that various approaches which are beneficial in development of strong gas sensors. I mean, it should be simple, like depositing a very small 5 nanometer film of, let's say, gold or silver, and in this case gold, and if you can improve and show it as a very strong, interesting gas sensing response, that's very easy to make, and it's scalable as well. You can go for a large area coating by this is very simple technique. Now we can see that the sensor response, now the operating temperature is reduced to 210 degrees centigrade, and now if you decorate them with gold particles, there is a clean, threefold enhancement in the sensor response. So you can see the first thing is that there is a strong enhancement in the sensor response. And of course, this sensor response increases with concentration, but we want to focus on a relatively low concentration of carbon monoxide gas. And you can see that this response time reduces from 28 seconds to 12 seconds just by depositing a nanoparticle thin film. And recovery time decreased from 60 seconds to 18 seconds, again just by, so you can see that as compared to a tin oxide film, 45 nanometer tin oxide nanostructure thin film, you just go for a plasmonic hybrid, there is a significant decrease in the response and recovery times. This is important for applications. Now, next thing is to check whether they are selective. You can see clearly that as compared to tin oxide, the gold tin oxide plasmonic nanohybrid film shows excellent selectivity for carbon monoxide. This work was published in Journal of Alloys and Compounds in 2016, and this is from Neha's thesis. So we have prepared these plasmonic hybrids, and they show enhanced carbon monoxide gas sensor response with a small response time, recovery time, and with very good selectivity, which makes them very promising sort of a material which can be grown even on a larger sort of area, and hence one can directly go for it. Now, in another work, we want to show that we want to demonstrate the other approach that's using ion beam engineering. Can ion beam engineering be used to tailor-made or to improve the carbon monoxide gas sensing response? So you know that energetic ions, they're exciting. Accelerators, ion accelerators in particular, they deliver a lot of energetic ions, and depending on the species and their energy, one can sort of tailor-make nanostructures, their size, their shape, and of course their organization. And we wanted to explore that whether ion radiation can be an excellent tool to tune this carbon monoxide gas sensor response to a desirably higher or enhanced level where you can go for sensor development. So we took a very simple approach in which we deposited 45 nanometer tin oxide film and by simple carbothermal evaporation, the same film which we have shown earlier, and we irradiated these films coated on substrates, of course, using 8 MeV silicon 3+ ions using the 3 million volt tandem pelletron accelerator at Institute of Physics, Bhubaneswar. And the dose was varied from 110 to the power 13 ions per centimeter square to 110 to 15 ions per centimeter square, which is a very relatively moderate dose. And with the machine there at Bhubaneswar, it doesn't take long. So it's a pretty quick exposure, and that's it. So we have an engineered nanostructure film, which you can prepare very quickly, and just need evaporation and just need exposure for some time. That's it. Now you can see that the AFM results shows the particles, nanoparticles film in case of pure tin oxide sample in 21 nanometer average size. And when you irradiate them with 8 MeV silicon 3+ ions, it develops nano rings. You can see that there are like you have nanostructures of average size 138 nanometer with a central hole that we call them nano rings, because you can see that they are decorated by nanoparticles. So you have holes decorated very clearly by nanoparticles taking the shape of nano rings. So you can fabricate nano rings of tin oxide just by engineering of a nanostructure tin oxide film. Now the XRD results, XRD patterns clearly show that the orthorhombic tin oxide, and there is an increase in crystallite size of tin oxide from 16 to 29 nanometer, whereas that for cubic tin it varied from 29 to 24 nanometer. I want to emphasize that we deliberately created a tin oxide combination by carbothermal reduction, because tin oxide combination is a metal semiconductor heterojunctions, which is beneficial for developing improved gas sensor. Now, when a metal particle comes in contact with the semiconductor, depending on the work function of the metal, you can see that there will be a sort of favorable situation where you can have improvement in gas sensor response. So we want to use this to our advantage, and on top of that, we wanted to sort of use ion beam to improve further their gas sensor response. This work came in 2015 in Material Research Express, again from Neha Bharat's thesis. So you can see that tin oxide nanoparticles were there in 21 nanometer average size in the crystalline film, which grew on irradiation, grew to a size of 29 nanometer by simple conventional Oswald repenning process which is very clear when you expose a nanoparticle system to energetic ion beam. Then in this case, we are using the electronic excitations because the film thickness is very small than the ion range. And so you see, when you do excite this nanoparticle film, there will be growth of nanoparticle size. That's the first response. And you can see that when you increase this ion fluence further to 114 ions per centimeter square, there are dome-like structures with average size 95 nanometers. So from 21 to 95, there is a clean growth of nanoparticle size. However, beyond that, at a fluence of 5 × 14 ions per centimeter square, nanoholes started emerging on these nanostructures. So this is nanostructure film started developing nanoholes. Of course, these big structures are still there and they're growing into bigger, like 125 nanometer. So these nanoholes emerged at a fluence of 5 × 49 ions per centimeter square. Now, if increase this fluence further, you can see these beautiful nanorings distributed almost uniformly across the film. And this is shown 5 by 5 micron, but they are everywhere. So we can engineer these nanorings of tin oxide. These are basically holes decorated with nanoparticles of tin oxide around them, and the size of this, the outer size is 138 nanometer, with the hole size is 49 nanometer. So you can see that there are beautiful nanorings which are developed, and so this is again confirmed from SEM image. You can see that there are these holes surrounded by nanoparticles, and the size of these increased from, you can see, 21 to 138 nanometer, whereas the surface roughness increased initially up to 4.7 nanometer, then decreased to 1.6 nanometer. So there is, once these rings develop, there is surface roughness reduces. Now, though we propose the growth mechanism, which was published in Material Research Express, and when you irradiate this nanostructure tin oxide film, first phase, there is growth of particles, because this 8 MeV silicon ions deposits a good amount of energy in electronic excitation into the film, which leads to the growth of these nanoparticles. This growth further, they produces dome-like structures sitting on the substrate. However, if you keep on increasing the fluence, then there is lateral mass transport, and it produces then whole nucleation inside these structures. So if you see from a perspective, you can see that this dome formation is there. Then you keep improving the fluence, there is this stress, the amount of stress it cannot handle, and there is lateral mass transportation in response to the deposition of huge energy and leading to the nucleation of holes. And this hole then increases in size, producing something like nano ring. So this nano ring formation process in tin oxide thing. We have explored this for other metal oxide systems, and yes, we under some sort of optimal conditions, we can tune and we produce nano rings and explore their gas sensing response. Here we are just here I am discussing about tin oxide as a case study. Now we wanted to see for that whether this is beneficial for carbon monoxide gas sensing. You can see that this is a very simple technique. Just deposit a film by simple thermal evaporation, and expose for a very small time. And if you can improve the sensor response, nothing like it. It's a film. It's a film which is scalable, which you can go for a large area sort of deposition as you like, as many as you like at one go. And hence, this is beneficial if it is if it is leading to an improvement, and it does. You can see that. In case of Prishta, and you can see this, that there's a huge improvement. First thing to note is that operating temperature has reduced from 210 to 140 degrees centigrade. You can see that it now operating at a lower operating temperature. You can see that the sensor response almost is hugely enhanced. This enhancement in the sensor response by 16 times is very exciting, because you have a nanoparticle film or you have a nano ring film. The difference is huge. You have very sort of improved gas sensor response, and now of course you increase the concentration, this sensor response increases, you know that, but we should focus on lower concentrations of carbon monoxide to save lives. And in fact, even if it's further, you can see that nanoparticle film and nano ring film, there is a remarkable difference. So it's the nano rings, if you produce, they lead to remarkable enhancement in the sensor response, and hence also you can see in the response time and recovery time. In the pristine, the response time is very large, 12 minutes. But if you go to nano rings, it is just 10 seconds, and same is true about recovery time. From 14 minutes, the recovery time drops to 12 seconds. You can see that this is a very simple technique. And you have now a carbon monoxide gas sensor which responds in just 10 seconds. Recovery is 12 seconds. And considering the scalability, considering the simplicity, this is exciting, and hence application ready. Now, what you see here is this one is almost going to be getting published. Minor revision has come just in So now you know that how does it operate? I mean, you know that when interacts with this sort of reducing gas, that leads to a reduction in this depletion region, and that leads to a change in the resistivity. So these are chemoresistive changes. So if you are exposing to an oxygen molecules or an oxidizing ambient, then there is increased depletion width or depletion region, and if you you expose to carbon monoxide like a reducing gas, it reduces this depletion region and hence decrease in the resistance. So these are basically gas sort of exposure driven resistance changes, and now it's a question of sort of tuning the crystallites, having the right mix of crystallite size, porosity, defect concentration, which is required and for the development of very efficient gas sensors. And you sense a toxic gas like carbon or lethal gas like carbon monoxide with a very higher sort of response and selectivity. That's what is required. You can always improve. There is always a room for improvement in science. What is important is that there is a very simple tool that you optimize this defect concentration, or what we call oxygen vacancy concentration. You should have tune structures which are two-dimensional, and you adequately dope, or you sort of create porosity in these nanostructures. That's the way. And that's where you see that the enhancement of sensor response is attributed to formation of nanorings upon 8 MeV silicon irradiation, which provides high surface area for adsorption of oxygen vacancies. Now, in conclusions, we have produced, in the results I shown here, of course, we work on an array of 2D materials, 2D material-based plasmonic hybrids. We are just have limited to studies on gas sensing, because we do a lot of work on catalysis, photocatalysis, water purification, and other things. But here it's just like the utility of 2D systems and adequate doping and ion beam engineering to develop sort of efficient gas sensors. That's what I thought I would focus on here and share with you. So now 1% copper doping in tin oxide nanosets shows improved gas response with a very small recovery and response time, high selectivity, and gold tin oxide nanohybrid. By producing these plasmonic nanohybrids, you produce hybrids of tin oxide nanostructures with gold, and that leads to improvement in the carbon monoxide gas sensor response. And of course, with very good selectivity and faster response and recovery time. Nanostructured tin oxide films can be engineered using ion beam into a film of nanorings. And this demonstrated significant enhancement in 16 times enhancement carbon monoxide gas sensor response with very fast response time and recovery time, paving way for the development of smarter or efficient gas sensors that win a planar geometry. So I would like to acknowledge my group. This is my group in the Prant University, Delhi. Of course, some of the students have graduated and left for postdocs. Some have joined faculty positions, and some are. So I thank all these. I'm on the funding agencies like DST, CSR, UGC, IUSC, and of course my organization. And I would like to thank all my collaborators who have participated in these activities, and thank you for your attention.
Thanks a lot, Professor Mohapatra, for such an insightful presentation. If there is any question from the participants, please, you can ask. Is there any question? There is one question it is showing Vandana Sinde. How one check stability of nanostructure samples?
Yeah, so it depends on an application. So if you want to see stability, it is always in context with some performance. Like if you want to talk about sensor response, so it has to be like that, like we check the sensor response. So stability has to be with respect to some application or some parameter you want to see. Otherwise, if you are talking about structural stability, then if you want to on aging, on some exposure to some conditions, you study structure using XRD, using Raman. I mean, it depends what you want to investigate. If you want that it has to be stable with respect to gas sensing application, it is gas sensing you have to check. If you want to talk about how good it is like optically, then you have to talk about optical response stability. That if your band gap is there, I mean, it should not undergo change. Stability has to do with its structure, its composition. So I mean that you got to see, got to check using, let's say, structure you want to see. That's why.
Thank you, sir. Is there any question?
Hello. Yes, sir. I have a question.
Yes.
Hello.
Yes, please.
Hello, sir. My name is Solly. I want to ask that how can you ensure that in particular your sensing chamber, suppose you take a reading of 100 ppm gas, then how can you sure that in your chamber 100 ppm gas is imparting on your thin film, let's say crystal or whatever the form is?
Yeah, you see, this gas flow, you know that there are gas flow controllers. So how do you study that? So you want to sort of flow a gas inside a chamber of a fixed volume, and this is the
Yes.
flow rate is there.
Yes.
Now if you are looking at exactly near the film, how much it is sort of heating. I mean, you see what happens. See, you create a vacuum and you put some gas. Now these gas molecules are going to
Yes.
sort of heat. Now, depending on the pressure, there will be probability. Now, if you want to measure how exact amount is sort of bombarding the sort of surface, that's it. If that's what you want, or because we want to develop sensors, and so if you are, then it has to be in saturation. I mean, so you are allowed to equilibrate, and then it is in dynamic equilibrium. But if you want to specifically on a random point, if you want to check at any random moment how many molecules are bombarding, that depends on the pressure, obviously. So you maintain that pressure, maintain that constant flow of gas. That's how we do practically.
Okay. Okay.
So, is there any question? We have 5 minutes still to have some questions, if anyone. Sir, one question is from my side, sir.
Yeah.
Did you check these materials? Yes, sir. Did you check these materials for the solar energy applications? Because SNO2 is widely used in nowadays for perovskite solar cell applications, sir.
One of my student, Jaspal Singh, he is now in Canada in Quebec University. He did check, but these are other materials in hybrids. Our one of the major activities these days, let's say last sort of a decade, focuses on development of various strong catalysts, photocatalysts. In that, of course, some antimicrobials. So I focus mostly on plasmonic nanohybrids and tailoring their optical response. So this tin oxide based solar cells we have not pushed that hard, but yes, there are an active ingredient in that we have used. Like Jaspal worked on TiO2 based plasmonic hybrids. So we used tin oxide as one of the components, but I will not tell that pure tin oxide we focused on that. Why? You know that tin oxide has a lot of applications, but for solar there are better solar energy, there are better applications. You can use them as one of the layers, but they are not the main materials all the time. But yes, if 2D material, 2D tin oxide, why not? One can of course check.
Yes, sir. Yes, sir. Thank you so much, sir, for such a insightful presentation and your means research work that you shown that will be very useful to the audience to see and work on that particular material for these type of applications. Like you focused your talk on the gas sensing. It is, sir, a very nice talk. Thank you so much, sir.
I thought I will change. I'll for a change. I focused on this. Still, I tell that this sort of water purification based activities are one of the major focus. But I thought last time, of course, I presented a lot of catalysis, photocatalysis. I thought, why not a change? Why not talk about another application of this? Anyway, I really appreciate Piyush and Professor Shah for the invitation. It was really good. In fact, I visited your place long back. It was really nice.
Thank you, sir. Now I invite my fellow research, Ms. Hemangi Oja, to deliver vote of thanks.
Good evening, one and all present over here. I am honored to extend a vote of thanks on behalf of Department of Physics, Saurashtra University, RAJKOT, Gujarat. Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati, VIBHA, and GUJCOST, Department of Science and Technology, DST, Government of Gujarat. First and foremost, I extend my deepest gratitude to our esteemed speaker, Dr. Dheeraj Kumar Singh, Associate Professor from School of Nanosciences, Central University of Gujarat, CUG, Gandhinagar, and Dr. Satyabatra Mohapatra, Associate Professor from Nanoscience and Technology, Head Multifunctional Nanomaterial Lab, Guru Gobind Singh, Indraprasth University, New Delhi, who have graced us with their expertise and knowledge in today's session of Vigyan Yatra lecture series. I take this moment to thank our patron and co-patrons, Professor Nilambari Ben Dave, Honorable Vice Chancellor, Saurashtra University, Professor Chaitanya Joshi, President Vigyan Gurjari, Gujarat Prant, Professor G.C. Bhimani, Dean Faculty of Science, Saurashtra University, Dr. Narottam Sahu, Honorable Advisor and Member Secretary at GUJCOST, Gandhinagar, Dr. R.G. Parmar, Registrar, Saurashtra University. We are extremely grateful to Dr. Vidyadhar Vaidya, National Governing Council Member, Vigyan Bharati, and former President of Vigyan Gurjari, and Professor Rahul S. Kundu, Professor, Department of Bioscience and Member of Board of Management, Saurashtra University. I also thank Professor Nikesh Shah, Head of Department of Physics and President of RAJKOT Unit of Vigyan Gurjari, Professor P.N. Joshi, Secretary Vigyan Gurjari, RAJKOT Unit. I thank Dr. Puneet Negi for chairing the session. I also thank coordinators of Vigyan Yatra, Dr. Aswini Joshi ma'am, Dr. Piyush Solanki sir, and Dr. David Dhru sir. Last but not the least, I thank all the participants of Vigyan Yatra. Once again, we will meet tomorrow again at same time. Thank you.